Assalamu alaikum. My name is Mohammed Ahmed. Today our problem is 2D steady convection. To solve this problem we will use Ansys software. To open Ansys software we have to type workbench in search bar and open it. This usually takes 40 to 50 seconds according to the speed of your processor. Problem of our 2D steady convection problem is that a fluid enters in a pipe of radius 0.06 meters at a constant velocity of 0.1 meter per second. Fluid has following properties: density is equal to 1.2 kilogram per meter cube, a thermal conductivity of 0.02 watt per meter dot Kelvin, specific heat of 1000 joule per kg dot Kelvin, and a viscosity is 1.8 into 10 raised to power minus 5 kilogram per meter dot second. Boundary condition that we have is the first 5.76 meter of the pipe length are isothermal and held at 300 Kelvin constant temperature. The remaining 2.88 meter of the pipe have a constant heat flux of 37.5 watt per meter square added at the wall. To do this we use Ansys Fluent, and the objective is to calculate and plot the velocity, temperature, pressure and Nusselt number variation in the pipe. Assumptions that we have take to solve this problem is that the flow is axis symmetric. This means that in cylindrical coordinates r, theta or z there is no variation in the circumference direction theta. So the geometry in the simulation is a rectangle as shown in the following figure, and also the flow is steady. As you see in figure, the first 5.76 meter length is 300 Kelvin and the other 2.88 meter length at a constant heat flux 37.5 watt per meter square. Inlet velocity is 0.1 meter second and the radius of the pipe is 0.06 meter, and this one is the axis of the pipe. Because the problem is axis symmetric, so we take only draw only rectangle. First we have to go into Fluent toolbox and select fluid flow fluent and drag it into project schematic. Rename it 2D steady convection. Our analysis is two-dimensional, so we right click on the geometry and select properties. This type of window will be shown, so we have to select 2D in analysis type. Right click on the geometry and open new design modular geometry. This will also take 10 to 15 seconds according to the speed of your processor or RAM. In tree outline we will select XY plane because we are going to draw our dimensions or rectangle in 2D, and in XY plane go into sketching toolbox and draw rectangle. For to draw rectangle, first we select the center point of this axis. If we go on the region 0, 0, then this type of P is shown, and then we have draw rectangle. As you know, our pipe is divided into two parts. First one is isothermal and second one is constant heat flux. So we will split this. Go into modify tab, select split, and on upper line or below line, go to constraint, and go to equal length. Then go to dimensions and give specified dimension to vertical and horizontal dimensions. First we will give h2 is equal to 5.76, h1 2.88, v1 0.06. As you know, our radius is too low or less than the length of the pipe, so we drag, move the dimensions. Now save this geometry, select, go into modeling, go into sketch, and go into concept and surface. From the sketches, apply base objects and then generate. This will generate one part, one body, and then you have to save your project. On desktop we will create our folder lecture, and rename the file 2D steady convection. Our file is saved. Now go to mesh and right click and select update. After updating mesh, select edit. go on meshing and generate by default mesh. After generating mesh, go into face meshing, select this face and apply, and then again generate it. Then go to sizing. In the toolbox, select edge. You will also set by edge by using shortcut key Ctrl E, and then select upper and lower edge by holding Ctrl. And give the element size 0.05 meter, and then generate the mesh. In the second step, you have to also give sizing to its inlet and outlet edges. Go to mesh control, sizing, right edge, left edge, and then apply and generate mesh. Top, bottom, right left. To right left edge, instead of element size, select number of division and divide into 30 divisions, and then generate mesh. After this, you have to give the named selections. Go on right side, select edge, and then right click and select create name selection and type it inlet. Select upper edge, right click, create name selection, isothermal or isothermal wall, you can type both names. Select this edge, upper, and give it name selection, heat, flux, select bottom both bottom edges, and by pressing Ctrl and give them named axis of pipe, create name selection, outlet, and last but not least, select face selector and select the face and give it a name, domain, and then generate mesh. In the geometry, select surface body, and in material we have to specify it's a fluid or a solid. Our domain is fluid. Select it and then generate mesh, and then again Control S or save the project. After it we close, go into setup and again update. After updating setup, select right click and update. As you know, our radius is of pipe is too less as compared to its length. Then select double precision option and OK. This type of window is displayed to you. Velocity flow direction 0.1. Select OK. Interior domain, type interior. Okay, isothermal wall, type wall and edit. As you know, at this point we are given with constant temperature 300 Kelvin, that is by default. Okay, outlet pressure, edit, and our outlet pressure is 0 gauge pressure, Pascal. We are not including gravity effect. Going to solution method, select scheme simple, gradient least square base cell base, pressure type standard, momentum second order of wind, and energy is also second order of wind. Solution and initialization, standard initialization, compute from inlet. In setup window, first we have to check mesh, that our mesh is okay or not. If there is no error, then it will give option done. Go to models and on energy because energy equation, because our problem is have boundary conditions like isothermal and constant heat flux, and we are doing convection, so we are interested in to find how much heat transfers or temperature distribution. So we will on energy equation. Our problem is axisymmetric. Select axisymmetric option, pressure based type, absolute velocity formulation, and steady state problem. Now go to materials and specify fluid air. We can also get different types of fluid from fluid database, or we can rename it and define its property that has been shown in your fluid problem. Density is 1.2, thermal conductivity 0.02, specific heat 1000, and viscosity 1.8. That is well similar to air. And then change or create and then close. Then go to boundary conditions tab and give its boundaries. Right click on axis of pipe, type it's an axis, that is by default selected. If you go on edit, it's an axis of pipe, you don't have to specify boundary condition, you just have to select its type. Heat flux, it is done on wall, so by default voltage select, and I go into edit option, go into thermal heat flux, give a value that is 37.5. okay, inlet velocity, type velocity inlet, go into edit, velocity specification method. We will use magnitude and direction and give a x and then initialize it. We have to specify in components form velocity, so we have select exit velocity 0.1 meter per second and select OK, and then select solution initialization, standard initialization, compute from inlet, and you can see on here that our initial values are same or match to our boundary conditions, and then initialize it. Okay, DAQ file, select skin friction coefficient. Okay, and then calculate. In this we have also select our convergence criteria, that is on monitors, residual, edit, as you can see at this point that calculation is complete. Pressing Ctrl S, save the file and go into Result tab, edit it. As we open the CFD post or results section, go into vectors plot and type velocity vector, go to location, select periodic 1, go into symbol size is 0.1, view, apply rotation, apply reflection, apply scale. Because its radius is too less, so we will scale it 10 times and then apply. Some students it's not able to see both sides. For them you have to go default transform, some students see this problem like this. For this you have to go to default transform and then uncheck instance info from domain, apply reflection, ZX plane, and then apply, and then your problem will get rescale. Go into contours, by temperature, location, periodic 1, variable, temperature, view, apply reflection, method, ZX plane, apply scale 1:10, and then you have to apply it and check velocity vector. You can see the temperature variation and check temp and go to contours, type pressure, variable, pressure, location, periodic 1, view, apply reflection, method, ZX plane, apply scale 1:10, then apply. This diagram will show you how your pressure vary. And then save the project and then close the tab.